Okay, so I want to show you one more example with our chain rule. So the first part of it is kind of a refresher of an old idea, and the second part of it is kind of a preview of a new idea that we'll see in the future. So it's kind of a fun problem. All right, so we're given this function, f of x is equal to 2 sine of x plus the cosine of 2x. And the first thing it asks us to do is to find the equation of the tangent line to the graph at the point pi 1. So tangent lines are something that we looked at towards the beginning of this unit. And remember, to find the equation of the tangent line, we start by finding the slope of the tangent line, which comes from the derivative function. So the first thing we would do here is find the derivative of this function. Okay, so that would be 2 cosine x. And then for the second piece, cosine of 2x, we'll have to use our chain rule on that. Okay, so derivative of cosine is negative sine. It's actually going to be minus sine of 2x. And then chain rule, we multiply by the derivative of 2x, which is 2. All right, and then just simplify this a little bit. So 2 cosine of x minus 2 sine of 2x. Okay, so that's our derivative. Now, remember, we're looking for the equation of the tangent line at the point pi 1. So our slope will be f prime of pi. So I'm just plugging pi into our equation. Okay, so we'll have 2 times the cosine of pi minus 2 times the sine of 2 pi. All right, so cosine of pi is negative 1, so it'll be negative 2. Sine of 2 pi is 0, so that whole term is 0. So our slope is negative 2. All right, so then if we're trying to find the line, remember we have y equals mx plus b as a slope-intercept form of a line. We just found that m is negative 2. All right, and then we just need to plug in our point to solve for b. So 1 is equal to negative 2 pi plus b, which means b is equal to 1 plus 2 pi. And then just putting it all back together, we'll have y is equal to negative 2x plus 1 plus 2 pi. And that will be the equation of our tangent line. Okay, so that's something that we've done in the past. Just wanted to show you that all of these new derivative properties that we've learned along the way can help us to find the equation of a tangent line as well. So we started off with tangent lines. We were using that big limit process, and then we learned the power rule and said, oh wait, these don't have to be such a long problem. But now also with things like our product rule, our quotient rule, our chain rule, we can use these to find our derivatives and to find the slope of a tangent line as well. Okay, so part B here, this is, like I said a moment ago, this is sort of a preview of some stuff that we're going to do in the future. So nothing like this part B would be on the second unit test, but this is more something that we'll be seeing more of on the third unit test, but just thought I would give you a little bit of a preview here because it's kind of fun to look at. So what we want to do in this part is determine the values of x on the interval 0 to 2 pi, at which the graph of f of x has a horizontal tangent line. Okay, so we're going to find where we have a horizontal tangent line. Now, if you think about a function, okay, let me just sort of pull out, well, let me just go down here. Okay, so let's just say sort of arbitrary function. Let's say we have something like that. Okay, I'm not saying that this is what our function in this particular example looks like, but it's just sort of arbitrary function. If we have a horizontal tangent line, in this case, that would be happening at these 2 points where we have a relative maximum and a relative minimum point, okay? So with a horizontal tangent line, the slope of the tangent line at that point is equal to 0, right? Horizontal line has a slope of 0. So if we're looking for where we have a horizontal tangent line, basically that means our slope is equal to 0, which would have to mean that the derivative is equal to 0 because the derivative just tells us the slope of the tangent line. So we just need to take our derivative that we found in part A, which is this guy, 2 cosine x minus 2 sine of 2x, set it equal to 0, and solve it out. Okay, all right, well, with this function here, we have a sine of 2x. Really the only way that we can solve this is by rewriting the sine of 2x with our double angle identity. So it's probably been a minute since you've done those, but our double angle identity for sine of 2x is the same as 2 sine of x cosine of x. Okay, that's our double angle identity from trig. All right, so this is then just 2 cosine of x minus 4 sine of x cosine of x. Okay, remember this is set equal to 0. So if we want to solve this, we just need to factor it. So we can pull out a GCF of cosine of x. Actually, we could pull out a 2 cosine of x, which would leave us 1 minus sine of x. All right, so setting each factor equal to 0, we have cosine of x is equal to 0, and then, oops, I'm sorry, I made a mistake here. This guy was a 4 sine of x cosine of x, so that should have been 1 minus 2 sine of x as our second factor. Sorry about that. Okay, so if we set that second factor to 0, we would have that sine of x is equal to 1/2. Okay. All right, so then just thinking about your unit circle, cosine equals 0 at pi over 2 and 3 pi over 2, and sine is equal to a positive 1/2 at pi over 6 and 5 pi over 6. So those would be our answers to this problem. Okay. All right, so we'll be doing a lot more like this part B in the next unit, where we're thinking about finding horizontal tangent lines, finding maximums and minimums, but it's kind of fun to look at now just to sort of get a glimpse of what we're going to be doing in the future. Okay. All right, guys, hope you enjoyed this video. As usual, email me if you have any questions.